Hello and welcome. My name is Noah Deer. This is Lesson 7 in Portland Community College's Online Math 254 Vector Calculus sequence. Today we're looking at limits and continuity. We are going to look at definitions of limits in two variables. We have looked at limits in for single variable functions in single variable calculus, and now we want to look at limits when we have functions with two variables. So what we're thinking about is if we have a point that we want to say we're approaching that point, so the x and y values, the inputs of the function are approaching a specific point x and y, then how do we do that on a surface when we could be coming from all sorts of different directions? So we'll be looking at that definition. We'll see that we can approach that point from different pathways, so we can say, is the limit the same no matter what path we approach this point from, or is it different? And then once we have a hypothesis from investigating a limit, can we prove that the limit is what we suspect it to be? We can then look at functions that are continuous or everywhere, or we can see functions, look at functions and determine where they are continuous and have ways of telling that quickly without having to take limits for every single point on the domain of the function. And then we'll look at some more complicated functions, piecewise functions in two variables, and see how we can get some strange behaviors when it comes to continuity and limits in those situations and how to address them. So our first section, limits in two variables, is our introduction. We want to look at what these limits in two variables are. We're going to look at some formal definitions, and then we'll jump into some examples to get a feel for what this all means. We want to investigate the concepts of limits and continuity of real valued functions in two variables. To do this, we need a working definition of the limit as the point x comma y approaches a point a comma b for the function f of x comma y equals some limit L, which we're assuming is a real number in the range of the function, right? Because f of x comma y outputs z values, real numbers, so we would expect the limit to output some z value. So we're doing this for some function f in two variables, some point a comma b in two dimensions r2 and some real number L. Before jumping to the definition, let's remind ourselves of the definition of a limit in a single variable. So the limit as x approaches a of f of x equals L, again a real number for a function f in one variable, some real number a in the real numbers, and some number L in the real numbers. So our definition is, definition 7.1.1, given a function f in one variable x, the limit as x approaches some real number a equals L in R. That is, the limit as x approaches a of f of x equals L if we can get the outputs of f to become arbitrarily close to L by bringing x arbitrarily close to a from either side but not equal to a. So there's actually a more formal definition, but this gives us everything we need for our purposes. So actually, let's not draw that. Let's just draw a picture of what we got here. So we have some a value on the x-axis. We have our function that's floating along here, and we have what's going on with the function as it approaches a. So as we move along this function towards a in the x direction, we're asking what are the y values doing? So we don't actually care what's going on here. This could be an open circle or a closed circle. Doesn't matter because we don't care what's happening when x equals a. We simply care what's happening as we approach a. So if we have some specific y value here, we see that the y values of the function are approaching y1 as x approaches a from both sides for this sketch that I've created here. The key concept here is that we must approach a from both sides to have the limit be the same from both sides for this limit to exist. We can talk about one-sided limits, but the general limit must approach a from all, in this case only two since we are in one dimension, directions. So we're going to take this into the higher dimension where we have our inputs are points, and we have to approach the point in question a comma b from all directions, not just from a single pathway or a single direction. To say that the limit as the points x comma y approach the single point a comma b of f of x comma y equals L means that the outputs of f must approach L from all directions. But it is actually more than this. For the limit to equal L, we need the outputs of f to approach L along any path within the domain of f. This means we could be following a linear path, a parabolic path, an exponential path, or any path imaginable, and all of these paths would need to output the same number for the limit to exist at that point. With that, let's take a look at the definition. So our definition is definition 7.1.2, given a function f in two variables, x and y, the limit as x comma y approaches some point a comma b in R2 equals L in the real numbers, that is the limit as our points x comma y approach the point a comma b of f of x comma y equals L if we can get the outputs of f to become arbitrarily close to L by bringing x comma y arbitrarily close to AB along any path but not equal to AB. So if we have some sort of surface here where there's maybe like a ridge like this, but it's flat. Maybe this ridge is kind of sloping down on the other side. But we have just a flat surface outside of this, and we're approaching a point at the apex of this ridge. We see if we're following along the ridge, we get that the limits are going to output a z-value different than if we're approaching from along the flat surface below the ridge. So we could be approaching the point in question from, say, just to the right of it, but we could think of that as just to the right of it along the ridge pathway, or just to the right of it below the ridge on the flat surface below. And we're going to get two different outputs here. So here we would say the limit doesn't exist. So this is why we're worried about the different pathways in question, as opposed to just from all the different directions, because we could have different ridges that make it so that the limit doesn't exist. So let's go ahead and look at how to investigate these limits. Section 7.2, Investigation of Pathways. Example 7.2.1, we are to investigate the limit as x comma y approaches 0, 0 for the expression x times y all over the square root of the quantity x squared plus y squared. So we're using this to highlight our definition. To start, we could say what happens along the x-axis. So if we want to, come on. Oh, it was just going super slow, of course. So if we're looking at the x-axis, this is when y equals 0. So we're doing a straight line pathway for this function. And when we do this, we're taking now the limit as x comma 0 approaches 0 comma 0 of 0 over the square root of x squared when we plug in 0 for y, which is the same thing as the limit as x approaches 0 of 0, which equals 0. So along the x-axis, our pathway is just having outputs of 0. Let's look at the y-axis now. So for the y-axis, we have x equals 0. If we're thinking ahead, we should get the same thing because of the x times y on top. So we have 0 on top again. Now we have the square root of y squared on the bottom. This equals the limit as y approaches 0 of 0, which is again 0. So along the axes, our z-values are approaching 0. And in fact, because of the expression, on the axes, the z-value equals 0 everywhere on these axes. Let's look at something like y equals mx. So these lines pass through our origin, 0, 0. And this allows us to all at once, not looking at a single straight line, but at any straight line that passes through the origin, given m being any constant. So if we do this, what we're going to do is we're going to write the limit as we have x comma mx, right? We're plugging in mx for y as this approaches 0, 0. So we plug in mx for y in the expression to get x times mx over the square root of x squared plus m squared x squared. And we'll go ahead and simplify this down. Since m is a constant and mx is approaching 0, all of this is the same as just saying x approaches 0 of mx squared. Here I can pull an x squared out and get x square root of 1 plus m squared. And then this equals the limit as x approaches 0 of mx over the square root of 1 plus m squared. And as x approaches 0 now, because the m over the square root of 1 plus m squared is a constant, this all just equals 0. So along any straight line path, we are still getting that the z-values approach 0. Let's now try something like y equals kx squared. So now let's look at a parabolic path. Here we have the limit as x comma kx squared approaches 0, 0. And so we get x times kx squared, inputting kx squared in for y, over the square root of x squared plus k squared x to the fourth. Again, since k is a constant, this is the same as just saying x is approaching 0. It's a single variable now, right? X is our only variable, so x is going to 0. We have kx cubed over, again we can pull an x squared out of the square root in the bottom to get x square root of 1 plus k squared x squared. Here we get the limit as x approaches 0 of kx squared over the square root of 1 plus k squared x squared. Now as x goes to 0, on the denominator we get 1, and in the numerator we get 0, so this is going to 0 as well. So along these parabolas, still getting that this is outputting 0. Let's look at the parabolas x equals, let's do, what do we want for a variable, n, y squared. So these are the parabolas, the sideways parabolas going in the other direction. Note that y equals kx squared does not take into account these parabolas. So we have the limit as, so my x is now ny squared, and y is just y. This is approaching 0, 0. So we get y, oops, we want ny squared in for x, y stays itself. We have the square root of n squared y to the fourth plus y squared, again plugging ny squared in for x above in our expression. This gives me the limit as y goes to 0 of ny cubed over, oops, I forgot a squared here, over y. I can factor out a y squared from inside the root, and its square root is y, times the square root of n squared y squared plus 1. This equals the limit as y goes to 0 of ny squared over the square root of n squared y squared plus 1. Again, this equals 0. So in all of these different paths, we're getting 0. This does not guarantee that the limit equals 0 because we have investigated, well, we have technically investigated an infinite number of paths. We've looked at all of the straight line paths, including the x and y axes, and we've looked at all of the parabolic paths that cross through the origin, but there are cubic paths, there are exponential paths, there are an infinite number of different kinds of paths that could pass through the origin. So this investigation here, while telling that there's a good chance that the limit is 0, it's definitely not a proof. It's just that along the paths that we've looked at so far. If I think about looking at different powers, let's generalize this. If I have y equals another variable, let's do d, x to the n. Okay, so we have an, oh wait, I already used n above, let's say x to the c. So now let's do this for any power function. So now I have the limit as x comma dxc in for y goes to 0, 0. Then on top we get x times dx to the c over the square root of x squared plus dx to the c squared. Actually, I'm going to rewrite this kind of similarly to how we had before. When I plug dx to the c in for y and then square it, we get d squared times x to the 2c. Just save me a step here. So this gives me the limit as x goes to 0, since we're down to just the variable x, of d times x to the c plus 1. Again, I'm going to factor out an x squared from the denominator to pull an x out of the square root. Inside the square root, I now have a 1 plus d squared x to the 2c minus 2. This gives me, right, it's a minus 2 because we factored out an x squared from that term, so we took 2 out of that. This gives me the limit as x approaches 0 of dx to the c over the square root of 1 plus d squared x to the 2c minus 2. So we actually have to think about this a little bit more carefully. If c is 0, for example, then we would get x to the negative 2, and this would be infinity inside here, and we would have to deal with this in a more careful manner. Let's see. Let's not worry about that. Let's assume that c is greater than 1, so that 2c minus 2 is positive, and that this is just going to go to 0. We could look at the negative c values as well, but we don't want to do that much investigation on this. We just want to get an idea. If we go through all of this and we get something that is not 0, then we would automatically know that the limit doesn't exist. But in this case, again, as we plug in 0, this goes to 0. The d squared times x to the 2c minus 2 goes to 0. So in the denominator, we have just a 1. And in the numerator, we get a 0, so this all equals 0. So along any power function, y equals d times x to the any positive power, the limit is still 0. We could do this where we could switch it and say x equals some constant times y to any power, and look at that as well. But at this point, I think we've got a pretty good investigation saying that this limit does approach 0. Let's go ahead and take a look at the graph and see what happens there. This will allow us to really see along any pathway what's going on. All right, so we've plugged in. We have the surface here. Can now see that this is a pretty smooth function. There is this weird wrinkle right at the origin, but really every way that I come at this, the z-value is 0, first of all. If we plug in 0, we do get 0 for the z-value. And every pathway that I can see here is doing that exact same thing. There's no ridges. is really what's going on. We'll look at the next example where we do get ridges and see that in the picture we'll kind of see that that limit can't exist along every, it can't be the same along every pathway, and therefore the limit does not exist. All right, so next is an exercise for you to give a shot at. So now you try. And go through the same kind of investigation that I did before. If you want to look at this as an example, look along the x-axis, the y-axis, any straight line path, the parabolas in y that are opening in the y direction, parabolas that are opening in the x direction. And you could do any power function. I'm not going to require it. I may go ahead and do it myself as I work through this problem, but I will show the solution here in just a moment, but pause the video and we will go through that. All right, so here we have the work that I've done. I've set x equal to 0, which gives me the limit as y approaches 0 of 0 over 0 plus y to the fourth, which equals 0. Note I just skipped going from the point going to 0, 0 to just y going to 0, since I've already set the x equal to 0 here. And I've done that in all of the rest of them moving forward as well. Then I try y equals mx. Note I didn't, so the first one, when x equals 0, this is going to give me the y-axis. I'm not doing y equals 0 explicitly because y equals mx, since m is any real number, that actually includes when y equals 0, the x-axis in it already. So losing that redundancy. Nothing wrong if you did it separately. So here, if I plug in mx for y, then we're taking the limit as x goes to 0 of m squared x to the third over x squared plus m to the fourth x to the fourth, which equals the limit as x goes to 0 of m squared x all over 1 plus m to the fourth x squared. Again, this is going to equal 0. I try some parabolas now, y equals k times x squared. This gives me the limit as x goes to 0 of k squared x to the fifth over x squared plus k to the fourth x to the eighth, which equals the limit as x goes to 0 of k squared times x to the third over 1 plus k to the fourth x to the sixth, which equals 0 again. So far, it doesn't look like there's been any weird things happening. All of these directions, all of our straight lines give us 0. Parabolas that open in the y direction give us 0. And then let's look at parabolas that open in the x direction. So x equals n times y squared. I get the limit as y goes to 0 of n times y to the fourth over n squared y to the fourth plus y to the fourth, which equals the limit as y goes to 0 of n over n squared plus 1, which equals n over n squared plus 1. So here we have something different going on. Because we had these y to the fourths in every term in the fraction, top and bottom, they were all able to cancel. So the n is any constant that we want. If n is 1, this would give us 1/2. If n equals 2, this would give us 2/5. So we see that the limit is completely different numbers based on which of these parabolas that open in the x direction we look at. And thus the limit does not exist. Therefore, the limit as xy goes to 0, 0 of xy squared over x squared plus y to the fourth does not, let's write out my words here, does not exist, which we often abbreviate just DNE. Okay, let's take a look at the graph and see what's happening with this. So as we look at this graph, we see that as we move along, so the red axis is the x-axis, and if we were to move along a parabola that opens in the x direction, it's going to approach a z-value somewhere between 0 and 0.5 up here, and on the bottom they're going to approach something between 0 and negative 0.5. But if we approach from any other path, like, well, if we approach from a straight line path, we're going to be coming at an angle here, and it's going to cut down into the 0 value if I'm coming along here. But if we're coming straight along here, then we're able to write along this wall in a way where the z-values are approaching something other than 0. And if we were on top of this ridge, then we're going to have the z-values approach 0.5. If we were coming from in here, then it might climb up and get to 0.5. So if we look at my n values over here, we see that if I'm looking at the limit as y approaches 0 of n over n squared plus 1 equals n over n squared plus 1, if n gets really big, this is approaching 0. So for really large n values, so if we have really tight parabolas, it's actually going to look like it's coming closer and closer to that origin, the z-value equaling 0, like we want it to. But for small n values, like n is 1, we get 1/2. If n is something really close to 0, like, say, 0.1, then I'm going to get 0.1 plus 0.1 squared is 0.1 over 1.01. So that's 10th over 1. I'm doing this math in my head. So if n equals, say, 0.1, then we get 1/10 over 1/100th plus 1. I'm going to multiply top and bottom by 100 to clear my little fraction, and I get 10 over 1 plus 100. So we get 10 over 101, which is about 0.1. I'm just trying to figure out how I get the 1/2. If I take, we got the 1/2 when n is 1, yes. So as n gets small, then these are going to ride back down the wall to when z is closer and closer to 0. So if I have n is small, we're down lower. We have wide parabolas opening up, so we're writing down this wall at that point. All right, so let's go ahead and move forward. So we now want to, if we look at the first example, like this example we just did, this exercise, the limit does not exist, so we're done. We don't have to prove anything. We've shown that along different paths we're not always going to get the same limit, so we've done what we have set out to do. For the first example, 7.2.1, we investigated enough to get an idea that it could be 0, and we can't find anything where it's not 0, but this is not a proof that it is 0. We now want to come up with a way of proving a hypothesis. So for that same example, where the limit as x comma y is approaching 0, 0 of x times y over the square root of x squared plus y squared, we have the hypothesis that the limit equals 0. So we set that hypothesis, and then we want to try and prove that the limit does in fact equal 0. If we can make a proof of it, then we're done. So let's give that a shot here. So the idea is this. If we want I'm going to write this over here, the limit as xy goes to 0, 0 of xy over the square root of x squared plus y squared. If this is what we're assuming, then say this was a 5 or anything else, we would subtract this over to the other side, forget the limit for just a moment, and have xy over the square root of x squared plus y squared minus 0. And we really want the difference between these, the size of the difference between these two numbers, to go to 0 for this limit to equal 0. So this is what we're going to look at. We're going to look at the magnitudes of the difference between the suspected limit and the expression in question. In this case, since we're subtracting 0, we're just going to be investigating the absolute value of xy over the square root of x squared plus y squared. So instead of looking at the expression itself, we look at the magnitude of the expression and show that the magnitudes are going to 0. So this, since the denominator is all positive, because x squared and y squared are both positive, this we can rewrite as equals the absolute value of x times the absolute value of y over the square root of x squared plus y squared. Let's notice also, since we're looking at the magnitudes, that these have to be greater than or equal to 0. Our goal here is we're going to bound these magnitudes by 0 on the left and then by 0 on the right to show that as x and y approach 0, that the expression has to be approaching 0. So, going to do a little finagling here. Note that the square root of x the absolute value of x equals the square root of x squared. And I'm also going to pull the absolute value of y off to the side real quick. And I'm going to put all of this inside the square root. I'll explain some of my motivations here in just a moment. So, a fact that we're going to use, and this is kind of a common thing that we do for these kinds of situations, so I knew ahead of time that I wanted to use something like the fact that x squared is less than or equal to x squared plus y squared. And we know that this is true since y squared is positive. So if I'm adding a positive number to x squared, I have to be bigger than just x squared. If I move the right side over to the left side now, I get x squared over x squared plus y squared is less than or equal to 1. And if I have something that is less than or equal to 1, its square root is also less than or equal to 1. So that implies that our expression here is less than or equal to 1 times the absolute value of y. So now, scroll down here, we have our absolute value bounded. We have 0 is less than or equal to the absolute value of xy over the square root of x squared plus y squared. And this has to be less than or equal to the absolute value of y. Now we can take the limit as y goes to 0 of all three sides. Really, the limit is x comma y goes to 0, 0. And we get 0 is less than or equal to the limit as x comma y goes to 0, 0. The absolute value is less than or equal to the limit as xy goes to 0, 0 of the absolute value of y. So we get 0 is less than or equal to the limit as x comma y goes to 0, 0 of the absolute value of xy over the square root of x squared plus y squared is less than or equal to 0. So by the squeeze theorem, we have that the limit as x comma y goes to 0, 0 of xy over the square root of x squared plus y squared must equal 0. So that's how we're going to do this proof. The exercise that I'm going to have you look at is going to take some of the same techniques. We're definitely going to use something similar to x squared is less than or equal to x squared plus y squared. Make sure that you're thinking about that as you're working through it. There are going to be some other techniques that are similar to this that are necessary. Work on it for 5-10 minutes, and if you're completely stuck, go ahead and pause and I'll start the solution and then say, all right, now that I've given you some hints, see if you can take over from there. You're also going to use that the equation z equals x squared plus y squared is an elliptic paraboloid, and as you approach, this goes to 0 as xy goes to 0, 0, because we're on an elliptic paraboloid. I can actually show you a graph real quick. Here we have z equals x squared plus y squared, and we can see this is a nice smooth continuous function, and as we approach 0, 0, the z value is approaching 0 from all directions. Okay, so you'll need that fact in your proof as well. So go ahead and give this a shot. Oops. I'll work out the solution and then walk you through it in a few moments. Okay, so here's my hint, is if we have x, or if we have any two numbers, a minus b, where a and b are both positive, this has to be less than the magnitude of a plus the magnitude of b. Right? If we're subtracting, we're going to get a difference. This is going to be smaller than a sum here. So I'm breaking this up where it's the addition of these two, so I don't have to worry about the subtraction. Everything here is positive, so I don't have to worry about the absolute values. And now we can deal with this and use some of the techniques that we saw above. So if you want to pause the video again and try this now, I'll go ahead and work out the rest of the solution, but see if you can get it from this point. And we're back with the solution here. So from the point that I'd left off, I note that x squared is less than or equal to 2x squared plus y squared. And if I divide this over, I get x squared divided by 2x squared plus y squared is less than or equal to 1. If I multiply both sides by x squared, I get x to the fourth divided by 2x squared plus y squared is less than or equal to x squared. Similarly, y squared is less than or equal to 2x squared plus y squared, implies that y squared divided by 2x squared plus y squared is less than or equal to 1, and y to the fourth over 2x squared plus y squared is less than or equal to y squared. So that means that the x to the fourth over 2x squared plus y squared plus y to the fourth over 2x squared plus y squared is less than or equal to just x squared plus y squared. And now we'll use that fact that I'd stated before we started the problem, that the equation z equals x squared plus y squared, this has to go to 0 as x comma y goes to 0, 0 because it's a parabolic ellipsoid. So now I can take the limit of all three sides. On the left we get 0. This is less than or equal to the limit of x as x comma y goes to 0, 0 of the absolute value of x to the fourth minus y to the fourth all over 2x squared plus y squared. This is less than or equal to the limit as x comma y goes to 0, 0 of x squared plus y squared. Since that right side is 0, we get 0 is less than or equal to the limit as x comma y goes to 0, 0 of the absolute value of x to the fourth minus y to the fourth. Make that a little bit clearer here. All over 2x squared plus y squared, which is less than or equal to 0. Therefore, our limit as x comma y goes to 0, 0 of the quantity x to the fourth minus y to the fourth all over 2x squared plus y squared equals 0. All right. Next section. Okay, it's section 7.4, continuity of functions in two variables. We want to establish some basic properties that polynomial functions are continuous everywhere, that really most functions that we run into, like exponential functions, logarithmic functions, trig functions, radical functions, rational functions, all of these are continuous on their domain. They're nice, smooth functions. It's only really when we look at something like a piecewise function or really get crazy with how we're building our functions that we end up with discontinuities that are within the domain of the function, right? We could use an absolute value function. That's going to give us like a sharp point. But generally speaking, most functions that we look at are smooth. So we want to establish that as a theorem. But before we do that, we want to talk about the definition of continuity. We're going to start by looking at the definition in one variable. So as with our introduction to limits in two variables, let us compare continuity of functions in two variables to the continuity of a function in a single variable. Definition 7.4.1. A function f of a single variable is said to be continuous at x equals a if and only if the limit as x approaches a of f of x equals f of a. We say f is continuous on some interval I if and only if f is continuous at every x in I. So this is saying that the limit, that we're continuous if the limit equals the output of the function, and that limit has to exist from both sides. That is, as x approaches a from the positive and negative side, that we get a limit, that limit is equivalent to the output of the function. When we're looking at a function in two variables, we want a definition which is analogous to the single variable definition. We want the surface of our two variable function to be smooth without having to pick up our pencil. We don't want any instantaneous jumps at any point from any direction. Thus, definition 7.4.2. A function f in two variables is said to be continuous at the point x comma y equals a comma b if and only if the limit as x comma y approaches a comma b of f of x comma y equals f of a b. We say f is continuous on some domain D, which is a subset of R2, if and only if f is continuous at every point a comma b in D. I'm realizing also as I'm speaking that I said a slight misnomer earlier, that a sharp point is not a discontinuity. But if we want a discontinuity, we would have to have some sort of hole in the graph or some sort of jump in the graph where we're defined at the point, but maybe the point is above the surface and disconnected from it, but it's still in the domain. So generally that's going to take some sort of piecewise function. So what we want to be able to do is know where we could potentially have a discontinuity and realize that with our basic functions that those are only going to happen with piecewise functions. And if we have the following functions that I'm about to list here, that it's going to be continuous on their domain. So for our purposes, we want to be able to quickly look at a function in two variables and determine the set of points for where it is continuous. To do this, let's note that the following basic functions are continuous on their domain: polynomial functions, radical functions, rational functions, exponential functions, logarithmic functions, trigonometric functions. With this in mind, we can use the following theorem to determine the set of points where many functions are continuous. Theorem 7.4.1. Suppose functions f and g are both continuous on their domain. Then the following functions are also continuous on their domain. If we multiply f times g, if we do f divided by g, and note that in this case g cannot output 0. If g outputs 0, then we're also going to have an issue here. We also have linear combinations, a times f plus b times g, where a and b are any real numbers. And we have composite functions f of g. So this theorem is a little bit redundant. We could use the list of basic functions, and that a composition function is continuous. Let me reread this. This theorem is a little bit redundant, as we could use the list of basic continuous functions, and that a composite f of g of continuous functions is also continuous to derive the other three facts, but it's nice to state them explicitly. That is, multiplication of functions is a polynomial type of operation. Multiplication is within a polynomial, so we could use plugging functions into polynomials to get multiplication of functions, and we could use the same kind of idea to get division of functions, and again the same kind of idea with af plus bg for linear combinations of these things. So we could have something like an exponential function, e to the x times y. We recognize that x times y is a polynomial. We've plugged that into a basic exponential, and since we're composite functions, if both of the functions in a composite function are continuous, then the composite is also continuous on its domain. So here we shouldn't have any domain issues. If I divide by another continuous function like x squared plus y squared, we shouldn't have any domain issues except for where x squared plus y squared equals 0, because now we have a rational function. Well, the whole thing's not a rational function because the numerator is not a polynomial. But the idea here is if we divide continuous functions, then we are going to stay continuous within the domain of the division. So as long as x squared plus y squared doesn't equal 0, we are all set. Let's take a look at example 7.4.1. Actually, read this note real quick. The important thing to remember about continuity of functions is that you have to look at the domain of the composite function, which may be different than the domains of either of the original functions. So again, in e to the x times y over x squared plus y squared, the composite function, or the division function, the x squared plus y squared, once we've put it all together, that needs to be, we need to look at the domain of that. So if I have example 7.4.1, let h, capital H of x comma y equal e to the x plus e to the y all over the quantity e to the x times y is both in the exponent, minus 1. So e to the quantity x times y minus 1 is all in the denominator here. We want to determine the set of points for which the function capital H is continuous. So the only place where we have a domain issue here, the numerator e to the x, that doesn't have any problems, plus e to the y doesn't have any problems, the addition of the two doesn't have any problems. In the denominator, e to the xy has no problems, subtracting 1 doesn't have a problem unless we have e to the xy minus 1 equals 0. So this could cause a problem. So if e to the xy equals 1, this means that x times y equals the natural log of 1, which is 0. So if x equals 0 or y equals 0, we have a domain issue. That is, the domain of capital H equals the set of points x comma y such that x doesn't equal 0 and y doesn't equal 0. With that in mind, by this theorem above, this function, capital H, is continuous everywhere other than when x is 0 and y is 0. So continuous on the set of x comma y such that x doesn't equal 0 or y doesn't equal 0, as long as neither of those are true. So if we want to take the limit, so for part B, find the limit as x comma y goes to 1 comma 1 of h of x comma y. Well, 1 comma 1 is not an issue on this function. It's not a domain problem. We know that we're continuous everywhere so long as x doesn't equal 0 or y doesn't equal 0. So the limit as x comma y goes to 1 comma 1 of h of x comma y, this we can just plug it in. Because we're continuous means that the limit equals the output of the function. And h of 1 comma 1 equals e to the first plus e to the first all over e to the 1 times 1 minus 1, which equals 2e to the first over, I'm not going to write that first up there, it's just 2 times e on top over e minus 1 all on the bottom. And that's it. We can take a look at this graph real quick if we'd like. And we see, sure enough, if we are not on the x or y axis, that we get a nice smooth function. Nothing crazy is going on here. So we are continuous everywhere that this function exists. So use the theorem to go ahead and look at this exercise, exercise 7.4.1. Let capital G of x comma y equal sine of the quantity x squared plus y squared all over x plus y. We want to determine the set of points for which the function capital G is continuous, and then find the limit as x comma y goes to pi comma 0 of capital G of x comma y. Go ahead and give that a shot, and I will work through the solution with you in a few moments. All right, the solution to part A is that the domain equals a set of points x comma y such that x does not equal negative y, and this is also the set of points for which g is continuous. Getting this just because the only problem that we see with this function where we're not having a nice continuous function is that the denominator of the fraction inside the sine function cannot be 0, so x cannot equal negative y or y cannot equal negative x. If I want to take the limit for part B, the limit as x comma y goes to pi comma 0 of capital G of x comma y equals capital G of pi comma 0, since the function is continuous everywhere other than when x equals negative y, and pi does not equal negative 0, so we can just plug in here. So this equals the sine of pi squared plus 0 all over pi plus 0, which equals sine of pi, which equals 0. We can look at the graph here, which I think is a pretty sweet looking graph. It's pretty crazy. So it looks like we've got all these spikes and everything, but it is perfectly continuous. These are just, these hills get, I mean, we have an infinite number of them as we move in here and how this function is set up, which is pretty sweet, but it really is continuous. There's no gaps or jumps anywhere. It just is this infinitely oscillating, hilly, crazy, almost tree-like looking surface, but totally continuous everywhere other than right along the line when x equals negative y. Here I'm looking straight up and down. Let's see if I can move this a little bit. There we go. So the line when x equals negative y is right down the middle of this. We have a domain issue. But coming up to it, we have no domain issue, so nice and continuous everywhere else. Pretty sweet. Okay, let's move on. Last problem. Last section also. 7.5, continuity of piecewise functions in two variables. So the great thing about theorem 7.4.1 is that it takes care of quote-unquote most functions that can be written in an explicit algebraic form. However, when we entered into the world of piecewise functions, we're no longer in a situation that this theorem can handle because of the freedom of possibility that piecewise functions allows. When creating a piecewise function, one may create all sorts of discontinuities by playing with the input expressions for different sets of points in R2. Here we take a look at one such example. So, example 7.5.1, determine the set of points for which f of x comma y equals either x times y squared over the quantity 2x squared plus y squared when x comma y doesn't equal 0, 0, or have it output 0 when x comma y does equal 0, 0. So if I look at this, we recognize that the only place that we really care about is when x comma y equals 0, 0. When we look at this point, we know that that's going to give us a domain issue in the top expression, but because we're defining it piecewise, it's no longer a domain issue, so it is in the domain. And we need to know, does the limit as x comma y approach 0, 0 of xy squared over 2x squared plus y to the fourth, does this equal, does this equal the output of the function 0? So this looks similar to a problem that we did earlier. There wasn't a 2, but exercise 7.2.1, the limit didn't exist, so I'm going to guess that this limit also doesn't exist. I'm going to try, say, x equals 0. If x equals 0, we get the limit as y approaches 0 of 0 over y to the fourth, which equals 0. And if I remember right, we had sideways parabolas. If x equals y squared, and I don't even need to do the generalization for all of these sideways parabolas, but if we have just this single sideways parabola, then I'm looking at the limit as y goes to 0 of y to the fourth over, if I plug in y squared for x right here, I get 2x to the fourth, or 2y to the fourth, I'm sorry, plus y to the fourth. The y to the fourths all cancel, so we get the limit as y goes to 0 of 1/3 third equals 1/3. So we're getting two different limits depending on the path that we take. So this limit doesn't exist at all. So now we have a discontinuity at this point because this point is now in the domain. So still we have f is continuous on the set of x comma y such that x comma y doesn't equal 0, 0. And that's it. That is our lesson for the day. Thank you so much for listening, everyone. I will talk to you again in the next lesson. Take care.